The very first one is from Mr. Kyuwoong Hwang. He's a senior director at Qualcomm AI Research in Korea. We all know how generative AI is just taking us by storm. Just a year into the release of ChatGPT, it's really democratized the use of generative AI. So now we'll actually hear from Mr. Kyuwoong Hwang about the intersection of tinyML and generative AI. I'm very excited to hear this session. Over to you.
Thank you for the introduction.
Thank you.
All right, thank you for the introduction, and yeah, it's good to see a lot of you people here. And I am very honored to be invited to give a talk in this tinyML conference because as you know, the Qualcomm is also a device company. We do a lot of things at the device. And today's title is about the future of AI is on device. I agree. I think that more and more technologies are coming from the cloud to the devices these days. And especially in these days, the Gen AI is one of the biggest impact on the AI and the community, the society. Now, today, I will talk about the infrastructure Qualcomm have, or also the examples of what we did to make these large models to run on these devices like smartphones. So we'll talk about and then I will talk about the enabled Gen AI technology at device. How does this will interplay with the cloud version as a hybrid AI? Okay. Before starting, I just briefly introduce what kind of researches we do at Qualcomm. We do these three types of researches: fundamental research and the platform research. Actually, the platform research is making tools or frameworks to make these large ML applications to run on the device more efficiently. For example, the AI/ML, AI Model Efficiency Toolkit. This is kind of a device. This is a tool. Then optimize and reduce the size of your network to make it run more efficiently at the device. And we also perform these applied research that is developing applications for certain specific purposes. For example, voice UI or video recognition and prediction. And our own efforts also need to use these platform tools. So these will help each other to improve both. Also, some of the fundamental research results will help improve the platforms, the tools, and also the applications. So this is the process of what we do. So when we found the important problems to solve, then we identify it and make a solution by inventing new methods. But that is not the end. We make those models to be optimized enough to run at the device by quantizing it, reducing the size of it. And also, there's a software compilation stage. This compiler actually considers the neural network architecture, and based on these dependencies, it decides the best runtime implementation. And also, it considers the Qualcomm hardware accelerators characteristics, and make the compiled runtime code to be most efficient for this accelerator and for the model computational graph. So that is very similar for like a human optimization. If you want to improve your model's runtime speed, then you may fuse some of the operators to reduce the indexing time. And some of those things are being done automatically by this software compilation. And it runs on the device and showed as a proof of concept of the idea. And then this goes to the ecosystem for the commercialization. we do this for our technologies, and also we'd like to make the users of the Snapdragon, the customers, also perform their new ideas to be implemented and goes to the device as a POC and to the commercialization. So we build the tools for that. So this is one of the examples. So we showed this at the MWC beginning of this year, and it generates an image by stable diffusion from given prompt in less than 15 seconds. It runs like 20 inference steps. Now it is not less than a year. We improved its performance a lot. I will show it more detail later. Okay, I believe that most of you already knows what is the Gen AI, generative AI. It generates some report for you or answer your query, or it generates an image from your given prompt, or even do the codings. So these things are changed the kind of structure of these AI these days a lot, because the previous AI is more like a perception recognition. Now it has more intelligence, so it can perform many of our work, and that is a very big thing. We depend on a lot on these large language models or large vision models these days, and if those are currently running running on the cloud, but let's see whether it can run near our environments on devices. So as the Gen AI, the market starting, so it's now starting an ecosystem. There are infrastructure provider. They provide the computational resources at the cloud or even at the devices. And some provides those foundation models, but the large models for general purpose, or some provides domain-specific models. For example, specifically generating some images or answer the knowledge base of a specific company. Also, there's an application provider. They leverage these provided foundation models or domain-specific models to build their own services. Or sometimes the application provider, they build their own models. So these ecosystems are starting, and these Gen AI actually impact many use cases, many different devices. In XR, it can generate these virtual worlds, and in automotive, it can predict the trajectory of pedestrian or other vehicles. Sometimes it requires a good understanding or reasoning of what the person is trying to do to know the trajectory. So just the voice assistant on phone, or making a report for you on PC, or even improving the IoT in a warehouse scale. All right, or even can be used in robotics. Not only generating these cute image, it can generate the trajectory of the joints of robots to control it. And if you see these a lot of applications that uses these large models, then you can find that many of them actually having the range of the 1 billion to 10 billion parameters. Now the technology device, we now will be able to run sorry. These number of parameters, large models at the device. So 10 billion parameters at device is possible. So many of these applications now can be run at device. Okay, so I will explain a couple of use cases, our examples, what we had to make large models run at the device. And before doing that, just briefly reminding the knowledge distillation. Or many of you already know this, but it is being used a lot of steps in our optimization. So just to recap it again. So the knowledge distillation has a large teacher model performing well, and rather small student model. And we will have some training data, not the full data, but part of the data, and it will be used to train the student model to produce the correct output by cross entropy. And also, we let these student model to mimic the intermediate behavior of the teacher model. So for example, this case, the logics. Not only the best output, the distribution of these logics, second, third, and whether it is more confident or it is hesitated, those informations are mimicked by the student model, and then student model training will be much easier and faster, and recover a lot of the performance of the teacher models. So this knowledge distillation, we will use this a lot. Okay, and moving these Gen AI from cloud to device gives a lot of important benefits. So it can be now private, and it can be reliable. It can run even in remote places. Latency is low, and cost is low. You do not need to pay some computational resources on the cloud, and energy can be reduced. And as it knows all those data near you, so it can be personalized to you, to your preferences. Okay, so I'll explain how we speed up the stable diffusion. So stable diffusion, there's a diffusion process. So this perfectly good image, by adding more and more noises, then it becomes a noisy image here. And the reverse process, by reversing the diffusion, we can generate from these random images, random noises, to a certain good image. If we start from the random image, then random noise, then random image will be generated. But if we give some input prompt, the description of the image we'd like to have, like a vase in Greek style, then we can get that image. In here, these input prompts will be encoded into latent space by clip text encoder here. And this U-shaped network, UNet, it will perform these denoising in multiple steps. In this case, for example, 20 or more steps are required to generate these good images. Then decoder is converting these generated image in latent space into RGB space. So the big problem here is that the center part, UNet, it runs 20 times, and its size is almost 1 billion. So that's a lot of computations. So to improve the speed, we modify the network a little bit. It's actually pruned the attention layers, attention parts modules from the input layer, and then the performance is dropped. To recover the performance, we perform the knowledge distillation, and then the performance is recovered. By doing this, we reduce the required computations, even model size and the peak memory. The second thing is that, so the 20 steps of iterations are too much. So can we reduce it? So the idea is that here, the teacher performs 2 steps of the denoising, and let the student mimic these 2 improvements of the teacher by just 1 step, by using the knowledge distillation. So it actually works. So it reduced the number of steps a lot. We can perform this multiple times, then it can be a quarter too. So from these pruning and step distillation, reducing number of steps, and adding a couple of more techniques, the overall speed is improved 9 times. So the baseline was 5 seconds. And because this is improved new Snapdragon devices, the speed is not 15 seconds, is reduced. Actually, there's other more things are there too. So the baseline is also improved to 5 seconds. Now it is 0.5 seconds. about half seconds it's produced the output. Okay, and what about the performance? The performance numbers you saw previous slides is a little bit worse, but as you can see here, these pictures, images, the lower images are from the stable diffusion, the original version, and the center is the prompt to generate these images, and the upper side, that is from these optimized, the fast stable diffusion. As you can see, there is not much distinguishable differences in the image quality. It is in the similar level. So we achieved like a 9 times speed improvement without sacrificing too much of the quality or performance. Okay, so yeah, this is the same prompt, and if you just press the generate button, the output is produced like in about half seconds. If you see more clearly, that it seems like running 6 steps to getting this output. Right, so what we did to get this much of improvements. So we say it is a full stack AI optimization from system sides, meaning this is algorithms. So from algorithm, we reduced the number of diffusion steps by knowledge distillation. And for model efficiency part, we optimized the model. We pruned part of the network and recovered the performance drop by using knowledge distillation. And this compilation that considers the network architecture and accelerators. And this hardware accelerator, in this case, the Qualcomm Hexagon NPU of Snapdragon Gen 3 mobile processor, that showed that very good performance here. So with this, the image generation just to take a half seconds at device. The next thing is about the large language models. This is maybe the most, the important one of the Gen AI models. So this large language models is autoregressive, meaning that so if you give this prompt here to recite the first law of robotics, then it will generate the answer here token by token at a time. So that looks okay, but because this large language model is trained to produce the next token, so it needs to have all the previous history of the tokens to generate the next one. But the big problem is that this model, the large model we use here is a Llama 2 chat. It's a 7 billion parameter model. And to generate a new token, the 7 billion parameters should be read from the memory. So that's a lot of memory access. So in this case, it is more memory bound. The memory bandwidth limited rather than the computation itself. So we need to reduce these memory access. What can be done? So the first thing we can do is reducing the model size itself. So from the floating point 16-bit resolution, we can reduce it integer 4-bit resolution by quantization. So that will reduce a lot of memory. And so we'll speed up and also reduce the power consumption, many good effects. But the problem is that we need to maintain the performance too. But sometimes this post-training quantization works well, but that was not the case for these large language models of these 4-bit quantization. So it didn't work well. The performance dropped a lot. So we did quantization aware training, again with knowledge distillation. Okay. The reason we use these knowledge distillation is that these 7B models, it takes a lot of multiple steps of training pipelines, and it requires a lot of training data. We don't have that. We don't have those training pipeline too. So we just use the same knowledge distillation approach here, So this is a small model, student model, not small, it is small, but also quantized to integer 4. So we have some limited size data set and train it to predict the correct next tokens with data set. Also, we let this quantized model to mimic the behavior of the teacher model here, the floating point llama 2. Then we got like a less than 1 point increase in perplexity and also accuracy-wise in solving some natural language problems. Its performance accuracy decrease is also less than 1%. So it is in the very similar range. Okay. Right. And that is not enough. Just that's like a 4 times reduction in memory size, but we need to reduce it more. So how can we reduce the memory access? And one approach is called as speculative decoding. So as I said, to predict next word, we need to all those previous history, but we don't have that. Can we get some kind of a draft, speculative, a little bit less accurate prediction of the tokens? We can do that by using this draft model. This draft model is very small. It's less than like 10 times smaller than the large target model. So it can access the memory like 10 times smaller, and it can produce these tokens quickly. So in this case, like 4 tokens are generated from this draft model. That can be done quickly. And those generated 4 tokens are given to the large target model. And large target model, using these as a history, and it generates some 4 or 5 tokens in parallel by just accessing these large memory, the weights memory, just once, and perform prediction of generating of these next tokens in parallel way, in a batch way. So it can reduce the memory access like if you use these 4 tokens here, then 4 times. But sometimes these draft models produced output is incorrect when these large models try to generate the token, and if those results are very different, then those drafts are rejected. But the part of the network, part of the tokens are accepted, so the draft can now resume producing more draft tokens from the point. So in that way, it actually works, because some of the cases when generating natural language, for example, English, as a matter of fact, for example, so these kind of fixed phrases, it's very easy to predict what will happen as a next tokens. So sometimes it's easy to predict, sometimes it's very difficult to what will happen next. So those easy part can be covered in many cases by the draft model and accepted wholly by this target model. So with that way, we can reduce the memory access of these large models by leveraging these draft token generation from this small model. Okay, so more 4 tokens are given to the target. All 4 are accepted in this case. And so it says the robot may not injure a human being. The first law well generated. And these 2, draft model and large model, can run on different devices on a SoC. So for example, the large models can run on the NPU, and the small draft model can run on the CPU quickly. Right? Okay. So yeah, that is a very good approach or structure. But the problem is that how can we train this small model? even if it is a small, it's a kind of like a 700 million parameters, and it is still the same architecture, in this case the llama or the similar large language models. So training those large models require a lot of data and training pipeline again. So yeah, we use the knowledge distillation again, to train this smaller model. And achieved like 20 tokens per second on Snapdragon device. And I will show some demo here, but before going there, we'll briefly explain this architecture. So the Llama 2 chat, that is large language models, and we will show two use cases. One is just chatting, the other one is making travel planning, in this case, like reserving an airplane. So for all these things to work well, there should be an orchestrator, and this orchestrator, and also there's task classification. If the task is about travel planning, then orchestrator using using the travel planner API and getting the travel information and add it to the prompt and give it to the LLM to get proper output. The input can be done by voice or text. And there's a mini LLM that performs the task classification. Okay, yeah, this is audio is removed, but this is the demo video. So this is the speed of the generation. So this is not slow; it is a pleasant speed. And some chatting, asking some activities in San Diego, and asking to generate an itinerary, asking some more details about activities fee. Those are well answered. And yeah, this was shown in the last month's Snapdragon Summit. Also, this can be used for like a travel planning. In the case, the orchestrator used the plugin and API, and that plugin using some travel information site API to get those flight informations. Okay, so in this optimization practice, we did similar approaches. So for system optimization, the algorithm side, this speculative decoding improved a lot, and the model efficiency-wise, this quantization to 4-bit, that helped. And also, again, the compiler that considers the network and the accelerator, and then accelerator. These four, the full stack, actually made it possible. The next topic is, so if we have a good working Gen AI algorithms on the device, and how can we interacting or coexist with the cloud? So for cloud, everybody knows that the Gen AI takes a lot of more cost than just some traditional simple web search. So it requires a lot of more computation. And there's more and more Gen AI applications are being used. And more users are now using these applications. So the required computational cost at the cloud is becoming larger and larger. So it may be not that easy to cover all the people and most of the applications. Yeah, the solution. Yeah, if we can move some of the load of the cloud to the edge, then we can make it well organized or more efficient. Yes, hybrid AI approach will be possible. So you can, again, reduce the cost and energy, more reliable, private, and personalized to you by using the data around you. So in this case, we believe that So everything, the device is actually facing the users. So this can be the center of these hybrid AI. It can receive the request or getting information from the environments based on the context. Then if certain activities need to be done at the device, then it perform it. If not, it is beyond its capability, then it will ask the cloud. So yeah, these are the hybrid of these two computing elements. And one thing to be sure is that this should be the seamless. The user do not need to know that whether the cloud is engaged or not. So for user, it is just a quick response, and yeah, in the background, sometimes the cloud is used. So there can be several approaches. One simple hybrid is that the cloud device just used to convert these sensor information from the microphone or image or video into textual form and send it to the cloud and receive the answer and generate speech by using the TTS at the device. That's a simple approach. And we can do some more advanced approaches. In this case, there is an orchestrator at the device. It knows the situation at the device, where the person is, and what kind of things happened before a couple of hours ago, and what is planned at later. All these informations are there. Then it can give contextual information added to the prompt, make an improved one, and send to the cloud to the LLM. And then LLM can give more reasonable, considering the situation, answer to this query. Or we can even go further. So we can implement a speculative decoding in this hybrid scale. So the device can be like a draft model. So it is sure that the performance of its output, then it just give the answer to the user. But if it is not clear whether this is the correct answer or not, then it can send these draft tokens or results answer to the cloud, and cloud will verify it. So in the case, the computation of the cloud can be reduced a lot. So this is a device cloud scale speculative decoding. That is one approach of this hybrid AI. Okay, I explained a couple of use cases that we did to optimize the network to run at the device. And now I will explain a little bit of this Gen AI, this Qualcomm hardware accelerators. One of the main things we are using is the Hexagon NPU. Hexagon NPU has these more specific subcomponents. Here, there's a tensor processing blocks. It has more higher bandwidth memory access because it will use more weights and the data, the memory. And there's also specialized Scala and the vector accelerators with a higher clock speed. So these all share the same memory, and so it is optimized for different input and workload to give the best performance in computation and also reduce the power consumption. And also there is another thing, the sensing hub. It is more like a really tiny kind of a block, but not that tiny. It is very powerful. It has micro MPU there, a couple of, two micro MPUs here, and also the DSP and the memory, and the already sensing ISPs there. So it can perform many detection work here. For example, the keyword detection or the face or image, face or person detections, even some acoustic environment detections to here. And these also that context hub can gathers all these contextual information, and it can be given to the LLM when giving query to provide the context. All right. So all these Qualcomm AI stack is named as a Qualcomm AI Studio, and it supports a lot of different operating systems. there's a system software for accelerating the drivers, and also the developer libraries, such as profilers and debuggers. And it supports many AI runtimes. One of them is a Qualcomm Neural Processing SDK, also the Onyx runtime, TF Lite, Lite Micro, and DirectML. Also supports many AI frameworks, TensorFlow, PyTorch, Onyx, and Keras. And these AI stacks covers also multiple devices, such as XR devices, or the handset, or the car, or the IoT, or even the cloud server, laptop too. Okay, here I show that as you already know, the Gen AI gives a lot of good possibilities already, providing a lot of benefits. Now the Gen AI is going to the device, and I explained that what we are currently doing to support all these Gen AI applications to run on Qualcomm device as well through the Qualcomm AI stack. And also, this device AI as a hybrid AI with the cloud will be the future format of the intelligence. Yeah, that's our thinking. And yeah, you can contact us with these slides. And yeah, thank you. And do you have some questions?